This should be Chem27DBlake. Right now it's Wednesday morning, and you should be on this here today, Wednesday. Well, I got to get this uploaded and get home first, but so I want to kind of throw all the stuff together for the rest of the chapter, which I've already been doing anyway. There is, from a previous chapter, figure 18, page 194, this periodic table of electronegativities. You need to use that to calculate dipoles, because anything under the 0.4 is nonpolar, anything over 1.7 is ionic, and anything between about 0.4 and about 1.7 is polar covalent. So nonpolar covalent, polar covalent, and ionic. We've already talked about this, but I'm going to apply it to the examples today. Where this is in your chapter, this chapter, where you're going to find it and refer to it, is page 265, figure 20, which is the end of this chapter here. And then when you just subtract them, you get ionic if it's over 0.7. If it's less than 0.4, somewhere between 0 and 0.4, it's basically nonpolar. So to some extent, just kind of depends situation to situation. That'd be nonpolar covalent. And if it's between 0.4 and 1.7, we're generally consider that, at least for predictive purposes, to be polar covalent. Okay, so we left off on these questions. Uh-oh, I lost track. This one here is where I left off. We were looking at the nitrite ion and what its molecular geometry is, or molecular shape, which was bent because of these electron pair here. And we were also looking at, you know, we had a dipole this way, leads to a molecular dipole this way, because they don't cancel here, they're not opposite. 44, this is where we're picking up. You know how to do this, the molecular geometry of sulfur dioxide? It ends up bent because this electron pair here is going to push down by a valence shell electron pair repulsion theory. You're not going to have an angle of 180 here and 90 and 90. It'll push them around to where it's closer to 120, 120, 120. So that is bent. And by the way, on this one, let's see, I'm looking on that table of electronegativities. Sulfur is about 2.6, or yeah, 2.6. Oxygen is about 3.5. So if I did 3.5 minus 2.6, it's roughly 0.9. That's polar towards oxygen, which means you've got a dipole this way and a dipole this way, and they don't cancel. So we're going to have an overall molecular dipole downward. So that molecule will be polar. Let's go to the next one. If you have ozone, it pretty much looks the same way, which makes sense because the central atom is oxygen. If we go back one, the central atom is sulfur. They're in the same family. So everything around them is going to look the same if you have an oxygen and a double lone, or a lone pair. A double bonded oxygen and a single bonded oxygen and a lone pair. And by the way, these are in resonance. And by the way, when I did that, to show resonance, I should have a bracket on that. See if I can move this over. No, I can't. Use brackets for resonance. We also use brackets for ions. Okay, but that's in resonance. And so this should look the same, really, since it's the same setup. Is this polar or nonpolar? Well, the oxygen have identical electronegativities, so there's no dipole here and there's no dipole here. If you have no dipoles to start with, you can't have a polar molecule. So it's completely nonpolar here. That part's different. What about sulfur trioxide? Well, you had to do the lowest structure first, and you're pretty decent at this. We're going to assume you know how to do this. You end up with the sulfite ion bracket, a 2- for the charge. It's all single bonds. There's a lone pair off the sulfur. Once you do that, it I don't have my molecular kits. I'm going to qualify this by saying I want to check it because this sure looks a whole lot like ammonia is. Okay, but it's an ion. Okay, we're okay. So it's going to look like this when it's done because you don't see that lone pair. And you have one down here, down here, down here. So that is trigonal pyramidal or trigonal pyramidal or trigonal pyramidal. I often say triangular pyramidal because that's what I talked about for 25 years or more than that, actually probably close to 40 years. Different books will use a little bit different terminology. So it looks like so with one of these removed, and I've got an electron pair, lone pair up top, and they push these other electrons and these other pairs down. That's what's called valence shell electron pair repulsion theory. Now, is that polar? Well, let's see, sulfur and oxygen, again, it's about, what did I say, sulfur's about 2.6, so oxygen's about 3.5, sulfur's about 2.6 in that table, page 265. That's about a 0.9 difference. That's good and polar. So you have a dipole towards oxygen, dipole towards oxygen, dipole towards oxygen. All those together don't cancel because they're not exactly opposite one another. They all add up a little bit downward, and that ends up with a molecule that has an overall polarity. So it is a polar, in this case, ion. It's a polyatomic ion, but it is polar. Sulfite ion is polar. Which makes sense because it's an ion, it's probably going to be water soluble. Okay, next one. 37. I don't know what pages these are all on, but you got a book. You should have a hard copy of the book out, flipping back. 37 goes somewhere before the 50s. We want to know about the molecular shape of this one is. This one ends up being trigonal planar. Boron does not follow the octet rule. It's sp2 hybridized. We'll talk about hybridization in more of the upcoming ones. This is sp2 hybridized. And it ends up looking like, where'd it go? Something like, these out. I got them all done, I just need to get out. Something like this. All in a plane, but in a triangle. Now, are these bonds polar? Probably. Looking on that table, boron is 2 about, and hydrogen's about 2.2. So actually this is not particularly polar. These are pretty nonpolar bonds here, pretty nonpolar bond here, pretty nonpolar bond here. But even if they were polar, in this case, they would cancel out. Okay, going on. 47, here's one that was expanded octet. And this molecular shape or molecular geometry is also trigonal planar. That one is this one for real. This atom that's in the center would be a chlorine atom in this model. So this is an expanded octet, which means you have more than 8. You have 2, 4, 6 shared, 8, 10, which would look something like this. Chlorine in the middle, fluorine, fluorine, fluorine. I should have green dots, green balls on here, but I've got them busy doing something else. And in a pair of electrons one way and a pair on the other side. So something like this. And you don't see the lone pairs. So what you do see is in a plane, you have a triangle in a plane. Triangular planar or trigonal planar. Or trigonal planar. Here's another one that is an expanded octet. You know, this ends up with PCl5, ends up with 40 electrons and 5 bonds. I'm not sure I can even do this one. Yeah, I can. Is this 5? 1, 2, 3, 4, 5. Okay. Yep, the one I just had in my hand, actually, we can do this with. I just had to add these back in. Okay, here's what you have. 1, 2, 3, 4, 5 atoms around a central atom. And the molecular shape or molecular geometry here is trigonal or trigonal, bipyramidal or bipyramidal. Okay, so here's a plane with a triangle in it like we just had. If I stick one on the top, let's say, then I have a little 3